Okay, a little cut off in the notes. You online watching this, go ahead and freeze the screen, write these down, and then we're going to move on. Okay, maximal path, finding one. Okay, and you can write those words down and then blah, 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 using the terms today. So we got to find sources and sinks, and then find all possible, starting at a source and ending at a sink. Those are all the individual maximal paths. Our first example, our first drawing of the day, does not have anything tied to it as a key. Like, what is this? What does this involve? Does this involve dressing myself? Are you going to teach me to dress myself again? Not really. But if I were, as you're writing this down, talking about this would be the putting on your hat, right? Where I circled T2. You okay over there? All right. Why? Remember what that's called? Starts with an I. What kind of task is that? Isolated. Or I would have taken, remember Hermie and Rudolph, which by the way is on Tuesday. If you guys want to, get your DVR out. Rudolph the Red-Nosed Reindeer. Nobody. Who's seen that movie a lot? They want to be independent. Remember that? All right. Good thing this is a great start to the video. Wake up over there! Did you miss me? All right. Now, what's this represent? This represents like one directed path of like getting yourself dressed in the morning. Remember, socks goes to shoes, right? And then those are kind of like an independent directed path. Has nothing to do with putting your shirt on, your underwear, or anything like that. All right. I really have a hard time finding the eraser on my pen. Okay, so drawing this. Now, I've accidentally put all the sources down. T2 is not a source. T2 is not a directed or a maximal path. It is an independent task, not part of this little procedure. But, and in order to get this job done, it is one of the tasks that has to be done. It just has nothing to do with talking about maximal paths, sources and sinks, and all that other stuff. So I've accidentally wrote, I don't know what the correct word is, the sources down, T1 and T4. What are the sinks? What are the enders? Well, two are easy. Look at the far right. What are two of our sinks at least? T10, 11. There's two more, though. T7, and then there's one more that you may not think is, but it is. T5. Okay? So these are all the sinks. T10, 11, 5, and 7. Wrote those in the order that, well, obviously T10 and 11 end because, they're all the way to the right and there's nothing after them. Well, T7 is an ender as well, and actually T5 just needs 3 and 4 to be done before we can do 5, and then it stops there. All right? And then, this has nothing to do with dressing ourselves. There is nothing tied to this. This is just a random digraph to, man, a lot of hiccups in this class. Okay, now... I'm going to have to scare somebody, scare the hiccups out of them. I picked the longest. I started at a source and I ended at a sink. Okay, so that is what's called a maximal path. And you list that as a listing of vertices. T1 to 3 to 6 to 8 to 9 to 10. So just exercising the verbiage. And then here's a smaller one. T4 to T5 was a very small maximal path. I had to put my socks on before I put my shoes. T4 to T5. Okay, and then of course there's others that I'm not going to highlight. Of course I could start at T1 to 3 to 6. Anyone listening? T1 to 3 to 6 to who? 7? I think that's my one down here. Yes. Or I could do T1 to T3, anyone? T1 to T3 to anyone? T5? And then, of course, the only one that's not played is T11. So it can't really start at T4. It can only start at T1. T1 to 3 to 6 to 8 to 11. Okay, so these are all the maximal paths. We'll show you what the purpose of this is, and you better, if you're paying attention, understand why we do this when we actually try to optimize a task. All right? All right. See? Now we're going to put weights on stuff. So pay attention to the next directed digraph. And then you'll see. All right, so the weight is time. What we're trying to optimize in any of these questions in Chapter 7, very short chapter, is optimizing a task, getting a job done in the least amount of time. So now on each task, we're going to assign a time or a weight to it. The weight of a path, then, again, we're talking about a maximal path or a directed path. The weight, actually, really maximal path, is a weight of a path that's the sum of the weights adding up all those vertices. And you'll make sense out of this. It's actually very simple. It seems more complicated than it needs to be now. Now here's the big word, many words of the day, but maximal path, of course. Critical path, which creates what's called a critical time. The critical path is the maximal path with the largest weight on it. Wait, Mr. S, we want to finish something in the shortest amount of time. Well, I'll tell you what that means when we actually have some context to this. Well, I'll actually tell it in the next example, even though it's not tied to a real-world example. What the critical path or the maximal path is, the one with the largest weight as you add the weights up, that is the minimum time that the job could physically be completed. Can't be completed any lower than that. The idea behind that is something we talked about last Tuesday. When we say a task is X minutes long, it cannot be completed any shorter than that, no matter how many people work on it. It's a perfect example of that, and that's the idea of it. I'm sure there could be some arguments in some of the things that we put up here, but you can't argue about cooking noodles. When you put noodles in boiling water, on the box it says it takes 8, 10, 9 minutes. It doesn't matter. It's not going to get done any faster. Boiling water is boiling water. The noodles will be done in that time, no shorter. You cannot make that go any faster. So that's the idea. When we put time on the task, that is the time for each individual task. Cannot be shorter. All right, so just remember that as we build these look at this graph and think about it. But so the finishing time is the time from beginning to end for the whole job. The whole job. Okay? It must be greater than or equal to the critical time. The critical time could be only the minimum amount of time a job is completed. And we'll talk about that with this next little graph here. And actually, I'll slide this up and pause the video. Go ahead and sketch this down. One more example that does not have a real-world tie-in to it yet. But before I stop the video, notice what's different. What's right next to T1? A big circle with what in it? 5. Yes, we don't have sync. I don't know where that came from, but okay. And what's that 5 mean? What's this 5 mean for T1? It takes 5. What do you think it's going to be? 5 what? Hours. Actually, that's what someone said first. Let's make it minutes, but hours might be a possibility too. I'm going to blabber on as you're writing this down. Remember, this is all a job. All these individual 8 tasks. Don't lose this task. There is one out here. What kind of task is TA called again? Starts with an I. Isolated or independent. It's not tied to anything else. That's like putting your hat on. Okay, so back to this. The only reason I highlighted this is T1 takes 5 minutes, T2 6 minutes, T4 10 minutes. And actually, I want you to look down here, and we'll answer that question now. If I only have one processor on this job, one worker, how much time would it take to finish this job? Well, I already put this. But don't you agree if you were just one person, I'd have to do task 1 maybe first and take 5 minutes. Then I'd have to move on to task 2 and take 6 minutes. Then I'd have to do task 4, maybe 10. And then basically one worker means add up all this time, 10, 16, 21, 31, 35, 36, 37, 38. It would take one worker a total of 39 minutes to get this job done because they are stuck with doing one task at a time. So I'm going to go through this again before we actually do the math behind what we're going to do, which is find the critical path, the critical time. What happens if I had two workers on this? Wouldn't you agree that you could start a worker on T4? How long does T4 take? 10 minutes. And while that worker is working on that, I could start somebody on T2, let's say, right? How long would it take to get these two tasks done then? Not 16 minutes, but how long? 10 minutes. But this is also what could happen. What happens after 6 minutes? What is that worker working on that? What can they do? They can start T1, or they could have started T6. I don't know. That's what we're going to work on tomorrow. Which one's the most optimal? Where do we go next? So now look at this. I could have one worker working on T2, then move on to T1, and then how long would it take to get these three jobs done? 11 minutes. But wait. T4 would be done in 10 minutes, and then what could this person do now? They could go even to what? T8. So how long would it take two workers to get these four tasks done at this point? 11 minutes, and now you're getting it. With one worker, it would have taken 22 minutes. But how I broke these up, you can see how this begins with two processors, easy for me to say, to turn into something much more optimal. All right, and that's why we're doing what we're doing. That's why we're going to find a critical path with a critical time to it, because with a certain amount of processors, we could get this job done in the critical time. I hope you understood that. Okay, now, only takes listening. Blah, 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 blah. Isn't that this one? Right? So what is that one? How much is that? Third hour didn't add, or they hate me and they won't tell me numbers. 16, thanks. Sixth hour. And then here's this. Okay, how much is that one? 17. And then I guess I have blue left. How much is that one? Is that 15? Okay, so Mickey Mouse example to explain this situation. Now, why are we ignoring, and then the last one, just 2 plus 1, 3? The only time an isolated task might come into play with this is if that isolated task was more minutes than one of these maximal paths, and it's not. So we'll have to somehow fit that one in there. So obviously, the critical time is 17 minutes. The more processors you have, it's possible to get this job done in 17 minutes. One processor, 39 minutes. That's what we're trying for, optimization. So that's why we want to organize. We want to organize how are the tasks lined up, who has an order requirement, and then from there, what is the optimal time? I just threw that word out there. That's tomorrow. The optimal time for this is getting the job done in the critical time, in that time frame, let's say. All right. Construct an order requirement diagram for the lasagna project. And I already gave you too much here. Determine all maximal paths. We're going to add to this. We're actually going to find out what the optimal time is, the critical time. Okay, now I did this for the students last year, so I just left it. Plus, I can't erase it because I don't have that old program. But you look at this, and go ahead and write this down if you want. You probably should. All right, because this really emulates a question very similar that you're going to see on Friday on your test. How am I supposed to know how this all groups up? First of all, I got to read them. Then second of all, okay, after reading them, brown the meat, add the tomato ingredients, garlic, and basil, then simmer the meat sauce. Oh, this all has to do with getting the meat sauce for the lasagna. So these are all tied together, with browning the meat being the source. I'd have to start that because then I add ingredients after I brown the meat. Usually brown and drain the meat, if you ever seen anyone cook. You want to drain the meat before you start adding other things. Less fat. Next, boiling the water. Does that have anything to do with browning the meat? No. Where does boiling the water come in? Oh, I boil the water so that I can cook the noodles because that's how I cook noodles. So those two are connected with boiling the water being the source of that directed path. So these are two separate directed paths I've already denoted. Then I got confused last year. Beat the eggs? Where the heck? Wait, do I have to make the noodles from scratch? Because you can make egg noodles using eggs for that. Then it says, oh, mix the beaten eggs with ricotta and Parmesan cheese. If you ever had, how many people have had lasagna? That's that chunky cheese, right? The thing that's in chunks, that kind of sits on top or as part of the layers, as opposed to the cheese that is melted and stretches. So this is a separate slice the mozzarella cheese and then assemble the layers and then bake. So I gave that all to the students last year so they could construct their own directed graph. Do so now with open circles because that's what I'm going to do next after you draw your directed graph. Each task is going to be given what? Or time. They said wait, which is good, but it's actually time. Okay, I did actually walk around the room. And then your picture doesn't have to look like this. I stole it from the book. What do you think this top number is here that I'm about to erase? Top left, T what? T1, which was what? What was T1 again? Brown the meat. Then what? Add the tomato stuff, blah, blah, blah. And then do what? Simmer. And then you have to let that happen. You have to understand cooking, all the flavors have to have time to develop with each other. Any cooking teacher would tell you that. All right? And then what does that become? One of the, if you look at your list. Ah! One of the, I have another sleep. I have sleepers in 6 hours. Yes. Good. I scared the answer out of you. But I got to worry about all my students, not just you. Okay? So it's one of the what? Starts with an L? Layers. Did you guys hear that? I have no idea what that was. And then you do what after the end of the layers being done? Bake it. Okay, so there's that path. Then we have a separate path. What was next? Oh, shoot. Boil the water. It does take time. You get it out of the sink. Then you put it on the stove, heat it. Takes a lot of time for water to start boiling. And then what do you got to do after you boil the water? Put the, what'd you say? T5, which is noodles, cook them, and then they become one of the layers, and then you bake it, and then you beat the eggs, violent, and then put the cheese with the eggs, and then that's one of the layers, and then it goes to baking, and then you cut the cheese, and then you put it as one of the layers, and then you bake it, right? Slice the cheese. Now what I'm going to do, don't write this down. Or, you already have your chart, or you don't because you don't take notes. Horse water, drink. Or not. Now we're going to put time on all of these jobs. Okay, so now you're not rewriting the whole chart. You can either do this or fine. But, I'm going to you want to bake it for 30 minutes because, again, as a cook, everybody knows that it takes time for things, the flavors to meld together. So that's why these times are set in stone. Again, hammering the point, it doesn't matter if you had 1 million people working on this. Simmering the meat sauce should take 30 minutes or you're going to affect the flavor. You're going to ruin it. Okay, boiling the water, doesn't matter how many people are working on it. So back in these open circles, I didn't see that chart. Well, you could have paused the movie and wrote it next to your chart, or I'll just reveal those right here. Now that we have a directed graph with everything tied together, all the paths connected the way they should be, the simmering the meat sauce path, the boiling in the noodles, the cheese with the eggs, and then the separate mozzarella cheese path. Now we could start talking about what is the critical time for this. By the way, how long would it take for one person to do this job? The answer is simple. The sum of all the times, because they can only do a task one at a time. That's what you need to think about as far as now the opposite of that is what's the optimal time? How fast can I get this done? So I had this down here. How long would it take for one processor, sir? Easy for me to say. I think it was 118. Did anyone do it? Did you add it up? Nice. So one person, 118. All right, but then trying to optimize this scenario. Just can't believe designers of certain things. Here's one path. Right? That is one maximal path. And that path now has a weight to it. T1 to T2, 10 plus 5, plus 30, plus 8, plus 30. 83 minutes. Fortunately, I forgot to erase. This ends up being the longest. But you need to check the others to make sure I'm right. Maybe I'm wrong, old and decrepit. Steven mishit that. There's another one. And that takes 58 minutes. 10 plus 10 plus 8 plus 30. Starting from a source and ending at a sink. I'll only highlight one more. Source to sink. This one is 46. Then the last one, T8 to T9 to T10 is our shortest. And actually least amount of tasks involved. Oh, very close to our shortest. Actually was, but yeah. Okay, so here's the idea. If I got 2 or 3 people working on this, they could start working on separate tasks, and then it could be possible that we could get this done in 83 minutes. So that is what finding all the maximal paths are, which means I could possibly get this done in 83 minutes. It can't be any lower than that, though. And again, I'm going to go back to that. T1 takes 10 minutes. You can't shorten that task. T2 takes 5. T3 should take 30 because you need those flavors to meld together. T9 does take 8, and then T10, you should bake it all for 30 minutes to let those flavors meld together. The minimum this could take is 83. The maximum it should take is 118 if you only had one person. That's the idea, and that's what we need to understand in the spirit of this section. All right.